In today's video, we're going to talk about what's called Hess's Law. And Hess's Law is another way, this is our fourth way of being able to find the enthalpy change for a reaction. So remember, one of them is taking the Q value, dividing by the moles. Another way is using bond energies. And then in our previous videos, we learned about enthalpies of formation. Okay, Hess's Law is basically a way of saying, look, it doesn't matter how you get to the enthalpy change for the reaction. You can get there any way you want. You can even use other equations to figure out the enthalpy change for a different equation. Okay, so basically what that means is you can combine multiple equations together to get the enthalpy change for another reaction. Okay, let me show you what I mean by that. So we've got three chemical reactions here, and we have the enthalpy change for all three of them. They're all combustion reactions. Okay, and basically what we're going to do is we're going to take these three equations here and we're going to combine them together to make this equation here. So what does that mean? It means that we need to take these three equations and somehow come up with 2 carbons plus 3 hydrogens to make C2H6. Well, how do we do that? Again, you can do anything you want to these equations. Typically what you're going to do is eventually we're going to add them all together. But other things you can do is you can double them, you can triple them, you can cut them in half, you can flip them one way or the other, and of course you can add them together. So what does that mean? It means that right here I need 2 carbon atoms. So basically all that I do, and I need them as a reactant, is so I go back up to the previous equations and I see the only spot where I see a carbon atom is right here, but there's only one of them, and I need 2 of them. So what can I do to make them have 2? I can double that chemical equation. So I can say 2 carbons, 2 oxygens, 2 CO2s, and what does that do to my enthalpy change? Well, now you have twice as much, so you're going to double that. So that becomes negative 786. Okay, and then I go to my next part of my reaction. I need 3 hydrogens. Now, if there's hydrogen in multiple places, then we're going to have to kind of mess around with it a little bit to make sure that we do it correctly. But again, the only place I see hydrogen is right here, and it is a reactant. Okay, because if it wasn't, then we would have to flip that equation, which we'll see here in just a minute. Okay. So this has 2 hydrogens, and it's the only spot there is. So now what I have to do is I need to take this whole equation here, and I need to multiply it by basically by 1.5. Okay, so that will give me 3 H2s, 3 halves of an O2, and also 3 waters. And then what does that do to my equation here? Sorry about that. I forgot to mute my phone there. Anyway, so now we have our 3, it's kind of hard to see, but there's our 3 hydrogens right there. There are our 2 carbons right there. So that we've taken care of. But now we need C2H6. Oh, I'm sorry. That's the one thing I forgot. I was in the middle of that. So what happens to our delta H here is we also have to multiply that by 1.5. Okay? So instead of 286 times 1.5 is going to equal negative 429. Okay? So now our last one, C2H6, notice that we need it here. We need it on the product side, but over here it's on the reactant side. So what does that mean? It means we have to flip that whole equation. So I'm going to rewrite it, but I'm going to put the products as reactants. So 2 CO2s, 3 H2Os, making C2H6 plus 7 halves of an O2. Okay, and then what does that do to our enthalpy change? Well, now it's the reverse reaction. So now instead of negative 1,560, it's now going to be positive 1,560. Okay, now if we've done this correctly, everything will cancel except this part right here. Okay, and by that, so remember, this is gone. We flip this around. So for example, we have 2 CO2s right here, and we have 2 CO2s right here. So they cancel. If they're on the reactant side and on the product side, they cancel out, kind of like with intermediates and rate laws almost. Okay, and you've got 3 waters. Here you've got 3 waters. Cancel, cancel. Okay, and now we have 2 O2s plus another 1.5 O2s, right? On the reactant side, you've got those 2 O2s plus another 1.5 right here. So that makes 3.5 O2s. And down here we have 7 halves, which is 3.5 O2s. So can you cancel those? Absolutely, yes, you can. Those 3.5 cancel with those and those 3.5s. And all we have left are our 2 carbon atoms. Again, kind of a mess. Our 3 hydrogens, and then our C2H6. Everything else has canceled. So now what do we do with our enthalpy changes? This one I do need a calculator for. Now we just combine them all together. So we take negative 786, subtract 429, and then we add 1,560. And this reaction is going to have an enthalpy change of 345 kilojoules per mole. Okay, so let me summarize that. If you double an equation, you double the enthalpy change. If you times it by 1.5, you times it by 1.5. If you take 1/2 of an equation, you cut the enthalpy change in half. Okay? If you flip an equation, you flip the sign of the enthalpy change. And of course, when you add the equations together, you add the enthalpy changes together as well. That is Hess's law right there. Okay, example number 2. A reaction called the thermite reaction, one that produces a lot of heat. It produces molten iron for welding railway tracks together. It's extremely exothermic. Okay, so we know that delta H is negative on that. It says calculate the enthalpy change in this thermite reaction, so that reaction above, given the standard enthalpies of formation of iron 3 oxide and aluminum oxide are those values. Okay. Now, enthalpies of formation means that we're forming things from their what? From their elements. So, they're not giving us the equation, but they're saying enthalpies of formation of iron 3 oxide. So, iron 3 oxide is Fe2O3, and aluminum oxide is Al2O3. And we need to form those from their elements. Okay, so we need to form Fe2O3. And we need to form Al2O3. Again, because they're enthalpies. So they're kind of combining enthalpies of formation here with Hess's law. So how do you form Al2O3 from its elements? Well, we've got 2 aluminums plus, and again, we just want 1 Al2O3. And so we're going to have 3 halves of an O2. And then for Fe2O3, it's going to look really similar. We're going to have 2 Fe's plus, again, 3 halves of an O2. Okay, and we know that the enthalpy change for this reaction is, let's see, so the aluminum one, it looks like, is negative 823, and the aluminum one, the iron one is negative 823, and the aluminum one is negative 1675. Okay, and now we can take those 2 equations and we need to turn it into this equation here. Okay, and this one's a little bit simpler than even that first one. Is notice that we need Fe2O3, but we need it as a reactant. And here we have it as a product. So what are we going to do? We're going to flip that equation. So we're going to make it, I'm just going to erase it and just write it the other way. So that's going to make it Fe2O3 becoming 2 Fe's plus 3 halves of an O2, and that makes it a positive 823. Okay, and then we need 2 aluminums as reactants, 2 aluminums as reactants, Al2O3 is a product, 2 Fe's is a product. What happens with our 3 halves O2s? They both cancel out. Okay, and so overall, now we just have this equation here. And what do we do with our enthalpy change? We take the negative 1675, so negative 1675, add 823, and we get an enthalpy change for the overall reaction of negative 852 kilojoules per mole. Okay, No values are given for the enthalpy of formation of aluminum or iron metal because they are in their elemental form. Okay, same thing with oxygen. Okay, O2, nothing that's in its elemental form will ever have an enthalpy of formation. Okay, part C. What would be the enthalpy change to convert 1 mole of aluminum oxide to 2 moles of aluminum using iron as the other reactant? So we want to convert 1 mole of aluminum oxide. So 1 mole of aluminum oxide. So basically, it's this same reaction. We want to convert 1 mole of aluminum oxide to 2 moles of aluminum using iron as the other reactant. So what are they saying here? They're saying the reverse reaction. If you're trying to take aluminum oxide and turn it back into aluminum, how much, what would be the enthalpy change for that? Well, for the forward reaction, it was negative 852. So for the reverse reaction, it'd be positive 852. All right, one more. I could stop the video here and make another video for one question, but we're just going to keep going here. Okay, calculate the standard enthalpy change for the reaction represented by the equation above. And all that they tell us is that the enthalpy of formation of water is negative 285.8. So you know that that to form water, H2O, from its elements, you would need H2 plus half of an O2, and the enthalpy change for that would equal negative 285.8. Okay? So, in this case, we're doubling everything to not have the 1/2 of the O2 there, and so we have to double our enthalpy change. So this is going to become 2, this is going to become 1, that's going to become 2, which means we have to multiply that by 2. So delta H would be equal negative 571.6. Okay, and that is kilojoules per mole of reaction, like always. Okay, calculate the amount of heat in kilojoules that's released when 10 grams of hydrogen's burned in air. So we're going to start with our 10 grams of H2, and then we're going to say there's 2 grams in 1 mole of H2. Now use the balanced equation. We're going to go from moles of hydrogen to moles of the reaction. So we're going to say 2 moles of H2 right here are used for every 1 mole of the reaction, and then 1 mole of reaction is 571.6. Again, don't worry about the negative in there. We'll get that here in just a second. Okay, so 10 divided by 2 again times 571.6 equals 1429. With 3 significant figures, it'd be 1430 kilojoules. And again, the question is calculate the amount of heat in kilojoules that is released. You can't release a negative amount, so it's just 1430. Okay, and then our last part here, part C, says given that the molar enthalpy of vaporization for H2O liquid is this. So that means that H2O liquid to vaporization means turning into a gas to H2O gas is equal to, delta H is equal to 44. What is the standard enthalpy change for the reaction? The same reaction, but now notice that that water's turning into a gas rather than a liquid. So up here, our equation, it's liquid. So how can we change this equation to turn it into a gas? Well, again, use Hess's law. So our first equation is 2H2 plus O2, making 2H2O, delta H equals negative 571.6. Okay, and this again is a liquid. So we want to cancel liquid and get salt and get gas, not solid. Okay, so we're going to have H2O liquid so that they'll cancel, becoming H2O gas. But notice there's 2 waters here. Here we only have the 1. So what do we need to do? We need to double that equation. And when we do that, this enthalpy change here, delta H is going to turn to 88 rather than 44. Okay, and so with it as a gas, now our liquids cancel. So now it's going to be a gas. we're going to take negative 571.6 and we're going to add 88, which means we get negative 483.6. Okay, so notice lots of combining things between enthalpies of formation and Hess's law. But again, the key is you can manipulate a chemical equation any way you want to make this work. You can double the equation, triple the equation, quadruple it, cut it in half, whatever you need to do. You can flip equations, and of course you can add equations together. And when you do that, you will come up with new enthalpy changes for that new chemical reaction.